Hello, everyone. Welcome to Soft Science. Tonight, we will talk about something that stretches the imagination as far as the universe stretches space itself. A question so vast, so beautifully puzzling, that it's been asked for centuries. Does space end? As you settle in for the night, allow your mind to gently float outward beyond the Earth, past the stars, beyond the galaxies, and into the most mysterious corners of the cosmos. This journey won't be rushed. We'll explore everything we know and don't know about the size, shape, and boundaries, if any, of the universe. This is a topic that calls for both scientific precision and poetic wonder. So let's begin. To start asking whether space ends is to begin contemplating what space actually is. And that's no small task. Space is not simply an empty void between planets and stars. According to modern physics, it's part of a fabric known as space-time, a four-dimensional continuum woven from the three familiar dimensions of space and the dimension of time. This fabric can stretch, bend, ripple, and expand. The deeper we understand space-time, the more we realize it's dynamic. It reacts to matter, energy, and even itself. Now, when we ask if space ends, we are really asking whether this space-time fabric has an edge, a boundary, or a limit. Imagine you're on a boat sailing across the ocean. You look to the horizon. It feels infinite. Water stretches out in every direction. But we know the Earth is round. If you kept sailing, you'd eventually return to where you started, having travelled around a sphere. Could the universe be the same? Could space curve in such a way that it has no edge, but is also not infinite? There are several possibilities. Let's start with the idea of an infinite universe. According to this idea, space just keeps going, forever. There's no boundary, no outer wall, no ending, only endless distance. You could keep travelling in any direction and never reach an edge. There would always be more space, more galaxies, more stars. This concept is supported by our current understanding of cosmic inflation, the idea that in the earliest moments after the Big Bang, space expanded faster than the speed of light. That sudden burst of expansion may have smoothed space into an effectively infinite expanse. However, infinity is a tricky concept. In mathematics, it behaves differently from finite numbers. An infinite space would mean an infinite number of galaxies, an infinite number of stars, and perhaps an infinite number of versions of you living slightly different lives. But is infinity real in the physical world, or just a useful mathematical abstraction? Some scientists argue that infinity may not exist in nature, that it's a sign we've hit the limits of our theories. Now let's consider the opposite idea, a finite universe. In this scenario, space is limited. It has a certain volume, a defined size, although, and this is key, it may still have no edge. This is where geometry becomes important. If the universe is curved like the surface of a sphere, it could be finite but unbounded. Just like how you can walk around the Earth without ever falling off an edge, you could, in theory, travel through space forever, looping around without ever encountering a boundary. This kind of curvature is called positive curvature. A famous analogy is a video game where the screen wraps around. Go far enough in one direction and you reappear on the other side. In a finite but unbounded universe, your spacecraft might do just that. Leave Earth in one direction and eventually return to it from the other, though the journey would take billions of years. Another possibility is that the universe is negatively curved, like a saddle. This type of geometry also allows for a boundless universe, but with a different kind of shape. In a negatively curved universe, parallel lines eventually diverge. This means the universe could still be infinite in size, but with a different structure than we'd imagine from a flat or spherical space. And then there's the case of a flat universe, which, surprisingly, is what current observations suggest. Measurements of the cosmic microwave background, the ancient afterglow of the Big Bang, show that space is flat to within a very small margin of error. This doesn't mean space is two-dimensional. It means it doesn't have large-scale curvature like a sphere or saddle. A flat universe could be infinite, or it could be finite with special topologies that wrap around in higher dimensions. But how do we know any of this? We can't just fly a spaceship to the end of space and take a photo. What we can do is look at light. When we observe the universe, we are looking at the past. Light takes time to travel. The farther away something is, the older the light we're seeing. The most distant light we can currently observe is the cosmic microwave background, emitted about 380,000 years after the Big Bang, nearly 13.8 billion years ago. But because the universe has been expanding all this time, the region that emitted that light is now over 46 billion light years away. That's what we call the observable universe, the part of the universe we can see. The observable universe has a radius of about 46 billion light years in every direction, giving us a sphere about 93 billion light years across. That's not the full universe. It's just the part we can see. Beyond that, space could go on, or not. It's one of the great unknowns. What lies beyond the observable universe? More galaxies, more emptiness, a wall. The truth is, we simply don't know. If space continues beyond our observational horizon, and most scientists believe it does, then there could be countless galaxies we'll never see, simply because their light hasn't had time to reach us. There's also a profound possibility that the universe is larger than infinite, in a sense. If space is part of a multiverse, a greater reality that contains many universes, each with their own physical laws and dimensions, then our entire observable universe might be just a speck, like a grain of sand on a beach. In such a view, asking if space ends becomes even more complex. We might have to ask, which space, which universe, which level of reality? Now let's zoom in for a moment and talk about the role of expansion. The universe is not static. Ever since the Big Bang, it has been expanding. Distant galaxies are moving away from us, not because they are traveling through space, but because space itself is stretching. This expansion is not slowing down. In fact, it's accelerating, driven by a mysterious force called dark energy. This means that some galaxies are moving away from us so fast that their light will never reach us. They are receding into a region of space forever beyond our observational horizon. This raises an eerie possibility. Someday the night sky could go dark. Distant galaxies will vanish from view as they cross beyond the cosmic horizon. The universe we can see will shrink, not because it's contracting, but because expansion is racing faster than light. Even if space is infinite, the part we can access will become smaller. Could this mean space has an effective edge? Not a physical boundary, but a limit to what we can ever observe, know, or touch? Possibly, but even this horizon is not a wall, just a point beyond which light can no longer reach us. In trying to imagine the end of space, we're also forced to confront the limits of human intuition. We evolved to navigate forests, rivers, and savannas, not infinite manifolds and four-dimensional curvature. Our brains aren't naturally built to grasp these ideas. That's why we rely on mathematics, physics, and imagination to explore them. Science extends our reach beyond instinct, giving us tools to peer into the great unknown. Some ancient cultures imagined the sky as a dome, with stars pinned to its inner surface. Others thought the universe was enclosed by cosmic walls or celestial spheres. Today, we know the sky is not a ceiling, but a window, a portal to a realm so vast it resists all boundaries. And yet, there's something comforting in the mystery. Whether space ends or not, we are part of it. Made of the same elements forged in stars, carried through time on a planet drifting through the black sea of cosmos. As we ponder where space ends, we also ask where we begin. So rest easy tonight. You are floating in a universe whose edges may never be known, but whose beauty, depth, and mystery invite you to dream beyond the stars. To deepen our understanding of whether space ends, we have to look not just at its vastness, but at its shape, its geometry and topology. The question, does space end, is intimately tied to how space itself is curved and connected. These are not just abstract ideas, they are central to the physics of the universe. Let's begin by thinking about geometry. In school, we learn about three types of basic geometry: flat, Euclidean, positively curved, like a sphere, and negatively curved, like a saddle. Surprisingly, the universe could adopt any of these shapes on a grand scale, and which one it chooses has everything to do with whether a space ends or loops back on itself or stretches infinitely. To test this, scientists measure something called the curvature of space. One method involves observing triangles, not drawn with rulers but formed by beams of light and massive cosmic structures. In flat space, a triangle's angles add up to 180 degrees. On a curved surface like a sphere, the angles add up to more than 180. On a saddle-shaped surface, they add up to less. By measuring the angles between distant galaxies and the patterns in the cosmic microwave background, astronomers can get a sense of the universe's large-scale geometry. And here's the remarkable thing: space appears to be flat, or at least so close to flat that the deviation, if any, is smaller than our instruments can detect. The European Space Agency's Planck satellite and NASA's WMAP mission both measured the curvature of the universe with exquisite precision, using the early light of the cosmos itself. The result: a universe that looks geometrically flat across vast distances. But flat doesn't mean simple. Flat space could still be finite, depending on how it's connected. This brings us to the concept of topology, how space is arranged and connected, even if it's not curved. A helpful analogy is to think of a video game screen. The game world appears to stretch out endlessly, but if your character moves off the right side of the screen, they reappear on the left. The space in the game loops back on itself. It's finite, but without boundaries. The edges connect. Some scientists speculate the universe might do something similar. It might be a 3 torus, a higher dimensional analogue of a donut shape where space loops around in multiple directions. In such a universe, if you could travel in a perfectly straight line, you might eventually end up where you started, although it could take billions of years and involve passing through the same galaxies multiple times from different angles. And if this were true, we might see repeated patterns in the sky, like the same galaxy appearing in more than one place. So far, we haven't found conclusive evidence of this kind of topological looping, but the search continues. Now, let's return to the observable universe, because this concept is often misunderstood. The observable universe is not the same as the entire universe. It is the region of space from which light has had time to reach us since the beginning of the cosmos, about 13.8 billion years ago. But because the universe has been expanding the whole time, the current size of the observable universe is actually much larger than 13.8 billion light years. It spans roughly 93 billion light years in diameter. This limit isn't a physical edge, it's a horizon, determined by time and the speed of light. Beyond this horizon, there could be infinitely more space, more galaxies, even structures unlike anything we know. But we can never see them because their light hasn't had time to reach us, and in some cases, never will, due to the accelerating expansion of space itself. Now let's explore how we even began to understand the expansion of space. In the early 20th century, astronomers believed the universe was static and unchanging. But that view was shattered by two discoveries. First, Albert Einstein's theory of general relativity introduced a dynamic view of space, one that could expand or contract, depending on the distribution of energy and matter. And in the 1920s, astronomer Edwin Hubble observed that galaxies were moving away from us, and that their speed increased with distance. This became known as Hubble's law. What Hubble saw was redshift, the stretching of light to longer wavelengths as galaxies recede. This is not because the galaxies are flying through space like bullets, but because space itself is expanding, carrying galaxies with it. It's like dots on the surface of an inflating balloon. The dots stay in place, but the surface between them grows. This expanding universe model gave rise to the idea of the Big Bang, not an explosion from a point into empty space, but a rapid expansion of space itself, starting from an incredibly hot and dense state. Every part of the universe was once compressed into a tiny volume, and as space expanded, that energy cooled, forming particles, atoms, stars, and eventually galaxies. Here's the key. If space has been expanding ever since the Big Bang, then its size is not fixed. It might be finite, expanding like a balloon, or infinite, simply becoming more infinite over time. If it's finite, we might one day be able to detect its shape. If it's infinite, there may be no boundary at all, just an endless cosmic plane with no walls, no fences, no endings. This brings us to a subtle but important distinction. The universe may be boundless without being infinite. It's hard to picture, but think of the surface of a sphere. A two-dimensional being living on that surface would never encounter an edge, but still live in a finite space. In 3 dimensions, something similar could happen. Space could curve in on itself, forming a 3-dimensional analogue of a sphere. Such a space would be finite in volume, but would have no edge, no outside. You could travel forever without ever encountering a wall. But now we must introduce another twist. The universe may not be the same everywhere. This idea is part of cosmic inflation theory. It proposes that in the earliest fractions of a second after the Big Bang, space underwent a rapid exponential expansion, far faster than the speed of light. This smoothed out the observable universe, explaining why distant regions look nearly identical in temperature and structure. But it also implies that inflation might not have ended everywhere at once. In some regions, inflation may have continued eternally, creating an infinite series of bubble universes, each with different physical laws. This is known as eternal inflation, and it suggests that our universe is just one pocket within a vast multiverse, a foam of universes expanding in different directions, possibly infinitely. If this is true, the question, does space end, becomes even more complicated. It depends on whether we mean the space of our universe or the larger space of the multiverse. And if that larger space is eternal and boundless, then there may be no ultimate edge, just endless bubbles forming within a greater cosmic sea. But even within our universe, boundaries are difficult to define. The concept of an edge implies something beyond, an outside. But space is not embedded in a larger container. There is no outside of space in which you can float. Space is not in something, it is the thing. Asking what lies beyond space may be like asking what's north of the North Pole. The question itself may not make sense. Let's now think briefly about what it would even mean to reach the end of space. Would there be a wall, a curtain of energy, a place where space itself stops? In our current understanding, that idea doesn't make physical sense. There is no known mechanism by which space could abruptly stop. Every model we have, from general relativity to quantum field theory, treats space as continuous. There is no natural termination point. Even in hypothetical models where space is finite, it still loops back on itself or exists within a closed geometry. An edge of space would violate the rules of physics as we know them. There's no border you could touch, no edge you could fall off. However, there are strange regions in space where the rules break down, such as the centers of black holes. Inside a black hole, space-time is crushed into a point of infinite density, called a singularity. Here, space and time, as we know them, cease to exist. Could such singularities be considered ends of space? Maybe. But they are not ends in a spatial sense. They are more like places where our current understanding ends. And perhaps that's the key. The question, does space end, is not just a question about the universe, it's a question about our understanding of it. As our tools and theories evolve, so too do our answers. There was a time when humans believed the stars were fixed points in a dome. Now we know they are suns, scattered across billions of galaxies. The deeper we look, the more we realize how little we know. And that, in itself, is a kind of beauty. A reminder that the universe is not limited by our imagination. So, as we ponder whether space ends, we are really asking a series of questions. What is the shape of space? How far does it extend? What lies beyond our horizon? And could space perhaps be infinite in every direction, or endlessly wrapping back on itself, like a grand cosmic maze? Wherever the truth lies, one thing is clear. We are living in a universe more mysterious and magnificent than anything we evolved to imagine. And even if we never find a final answer to the question of space's end, the journey to understand it brings us closer to the essence of what it means to explore. Not just the cosmos, but the boundaries of human thought. To better understand whether space ends, we need to return to a fundamental observation. The universe is expanding, but this expansion is not simply a slow drift of galaxies away from each other. It is a transformation of the very fabric of space itself, and it has profound implications for the nature and potential boundaries of the cosmos. Let's take a moment to revisit what we mean when we say space is expanding. It's easy to imagine galaxies flying through a fixed void like fireworks through the night sky. But that's not what's happening. The galaxies themselves are largely at rest with respect to the space around them. What's changing is space itself. It's not that galaxies are moving through space, it's that the distance between them is increasing because space is stretching. You can imagine it like this. Picture raisins in a rising loaf of bread. As the dough expands, every raisin moves away from every other raisin, not because the raisins are moving, but because the dough between them is expanding. The more space there is between galaxies, the faster they appear to move apart. This is exactly what we see when we look at the light from distant galaxies, a redshift that increases with distance, revealing how space itself has grown over time. This concept is called metric expansion, and it's not limited to galaxies. It applies to all of space. The very grid that defines distance, the invisible scaffolding of the universe, is being pulled outward. And the farther we look, the more dramatic this effect becomes. In fact, the expansion of space leads us to a paradox of sorts. There are regions of the universe so far away that their light will never reach us, not even if we wait forever. Why? Because space between us and them is expanding faster than the speed of light. While nothing can move through space faster than light, the expansion of space itself has no such limit. This means some parts of the universe are forever beyond our reach. This creates something known as the cosmic event horizon. Just as a black hole has an event horizon, a boundary beyond which nothing can escape, our universe has a cosmological horizon beyond which we cannot see and never will. Galaxies beyond that horizon are lost to us forever. They will continue to exist, but their light will never be able to catch up with the expansion of space. Does this horizon mark the end of space? No, but it marks the end of what we can observe. The true size and shape of the universe could be far larger than the observable portion, perhaps infinite, or perhaps looping back in a way we can't yet detect. Now let's consider another layer, the speed of light and the age of the universe. We often hear that the universe is 13.8 billion years old. That means the farthest light we can see, the cosmic microwave background, has travelled for 13.8 billion years to reach us. But the distance to the source of that light is not 13.8 billion light years. Because space has expanded during the journey, the region that emitted that light is now over 46 billion light years away. This is why the observable universe has a radius of about 46 billion light years and a diameter of roughly 93 billion light years. Beyond that, we don't know. We cannot see farther because light from those regions hasn't had enough time to arrive. But most cosmologists believe there is much more out there, perhaps infinitely more. So where does this leave us in our central question? Does space end? It helps to think of space not as a thing that can end, like a room with walls, but as a field of relationships between things. The universe is not a box sitting in a bigger space. It is everything. All of space, time, matter, and energy. If space ends, it must end within itself. But how can a thing be its own edge? This is why many physicists believe that space either has no edge, because it loops back on itself, or is infinite. In either case, there is no place you could go where space stops. There is no wall, no cliff, no glowing boundary line. If space ends at all, it ends only as an idea, not as a location. Still, there are alternative views. Some speculative theories in physics suggest that our universe might be a brane, a three-dimensional surface embedded in a higher dimensional space. This idea comes from string theory and brane cosmology. In such models, our universe is like a soap bubble floating in a higher dimensional bulk. If that's true, there could be other bubbles, other universes, nearby in that bulk space. Some might even collide with ours, causing enormous disruptions that could, in theory, leave imprints we might one day detect. This raises the possibility that space does have a kind of edge, not a traditional boundary, but a limit to our 3D slice of a higher dimensional reality. The trouble is, we have no direct way to test this yet. Higher dimensions, if they exist, are beyond our perception, and yet indirect evidence might someday emerge. One proposed signature is found in the cosmic microwave background, the afterglow of the Big Bang. If our universe were shaped like a torus or embedded in a larger bulk, we might see patterns in the CMB, circles or symmetries that repeat. So far, observations haven't revealed such patterns, but data is limited and new instruments are constantly improving our cosmic vision. Another wild idea is that the universe could be holographic. This doesn't mean space is fake, like in a science fiction movie. Rather, it suggests that the three-dimensional space we experience might emerge from more fundamental two-dimensional information encoded on a distant surface, like a cosmic hologram. In such a model, space could end not by reaching a wall, but by dissolving into more basic bits of information. It's a deeply abstract idea, but one that's gaining attention in theoretical physics. Regardless of the ultimate truth, what's clear is that our models of space rely on the rules of geometry, the nature of time, and the properties of light, and they work best when applied to the observable universe. Beyond that, we are extrapolating, guessing, with increasing uncertainty. Let's now reflect on the role of dark energy. In 1998, two independent teams of astronomers discovered something astonishing. By observing distant supernovae, they found that the expansion of the universe is accelerating. Instead of slowing down due to gravity, the fabric of space is stretching faster and faster. This discovery earned a Nobel Prize and introduced the mystery of dark energy. Dark energy appears to make up about 68% of the total energy content of the universe. Its exact nature is unknown, but it acts like a repulsive force, pushing space outward. This means that over time, distant galaxies are not only moving away, they're accelerating away, eventually disappearing from our observable universe. In the far future, the universe could become increasingly lonely. All galaxies not gravitationally bound to ours will fade from view. If this expansion continues indefinitely, we may be left in an island of stars, surrounded by blackness, unable to observe the past or detect the full extent of space. This is sometimes called the cosmic isolation problem. Future civilizations might conclude they live in a static, small universe, simply because everything else has drifted out of sight. They would never know the truth, that the universe was once vast, full, and rapidly expanding. Here again, we encounter an edge, not of space, but of experience. The boundaries of what we can know, see, or prove. The more we study space, the more we realize how much lies beyond our reach. Still, there is one more possibility. A universe that doesn't expand forever, but eventually collapses. In earlier cosmological models, scientists considered a big crunch scenario, where the expansion of the universe would slow, stop, and reverse. Space would contract, galaxies would converge, and everything would end in a final singularity. In such a universe, space would be finite in time as well as size. But with the discovery of dark energy, this scenario seems unlikely. The universe is not slowing down, it's speeding up. The current evidence favors a universe that expands forever, growing colder, darker, and more diffuse over time. So, if space does end, it may not be in a dramatic wall or crunch, but in a slow fading of visibility and matter. A universe that never ends, but becomes increasingly empty. In all of this, we come back to a central theme: our place within this vastness. You and I are tiny creatures, floating in a sliver of time and a pinprick of space. Yet somehow, we are able to ask these questions, to wonder about infinities, to map the curvature of existence, to listen for echoes from the beginning of time. That ability to ask if space ends is perhaps more miraculous than the answer. It means that we are part of the universe trying to understand itself. So as we continue to explore the cosmos, we carry a quiet truth. Even if space does not end, our understanding of it is always expanding. We move forward not with certainty, but with curiosity, lighting a candle in the darkness and watching the shadows shift. To continue our journey through the question, does space end? We now turn our focus inward, not to the borders of the universe, but to the theories and evidence that attempt to describe the shape and origin of space itself. To understand where space might end, or whether it even could, we need to explore the very earliest moments of the cosmos. Everything we know about space begins with the Big Bang, but it's important to clarify what the Big Bang was and what it wasn't. The Big Bang wasn't an explosion in space bursting into some pre-existing void. Instead, it was the rapid expansion of space itself. It didn't happen at a particular location in space. It happened everywhere at once. Every point in space today was once part of that hot, dense origin. At time zero, the entire universe was compressed into an extremely dense and hot state. A singularity, in mathematical terms. This moment, as best as we can describe it, marked the beginning of the expansion of space. But does that mean it was the beginning of space itself? That's still an open question. General relativity describes the universe remarkably well from about 1 second after the Big Bang onward. But before that, especially as we approach the first 10 to 36 seconds, classical physics breaks down. We need a quantum theory of gravity to understand what came before, and we don't have one. Not yet. That's where speculative models like loop quantum cosmology, string theory, and quantum fluctuations of space-time come in. These are attempts to peer behind the veil of time itself, to understand what happened before the universe as we know it existed. One such idea is that the Big Bang was not the beginning, but a kind of bounce. According to this view, the universe might have contracted before it expanded, going through a prior phase of existence that ended in a crunch, followed by a rebound. In this cyclic model, space doesn't end, but it changes. It pulses, expands, collapses, and expands again, endlessly. In another theory, the Big Bang emerged from a quantum fluctuation in a pre-existing nothingness. In the quantum realm, even empty space is teeming with uncertainty and possibility. The fabric of reality itself may be unstable at microscopic scales, occasionally producing tiny bubbles of space-time that inflate into full-blown universes. In this view, space did not come from a point, but from a fluctuation, an inevitable flicker in a deeper cosmic sea. Both ideas have one thing in common. They push the question of the end of space into a new domain. Not outward, but backward. If we follow the story of space to its beginning, we still don't find an edge. Instead, we find mystery, a region where our current understanding of physics gives way to uncertainty. And that brings us to another fundamental question. What is space made of? We often think of space as a background, a stage on which the universe plays out its drama. But modern physics suggests something more radical. Space itself may be emergent. That is, space may not be a fundamental ingredient of reality, but a phenomenon that arises from deeper, more basic elements. Like temperature arises from molecules, or waves arise from water. This idea is explored in quantum gravity theories, especially in the concept of space-time emergence. According to this view, the geometry of space is not built into the universe at the ground level. Instead, it's something that appears when countless tiny quantum events interact in just the right way. Like a pattern emerging from randomness, space may crystallize from the collective behavior of information or energy. This has profound implications. If space is emergent, then asking, where does space end, may be like asking, where does the sound of a violin stop when the strings are still? It may not be a question with a well-defined edge. Instead, there may be conditions under which space no longer makes sense, where the fabric of space-time dissolves into something more primitive. One leading proposal along these lines is the ADS-T correspondence, often referred to as the holographic principle. It suggests that everything that happens in a volume of space, including gravity, can be described by information encoded on a lower dimensional boundary, like a hologram. Imagine then that the space we move through is a projection, a high-fidelity illusion built from fundamental bits of data on a distant surface. In such a universe, the end of space would not be a border, but a loss of information, a region where the projection fails or simply doesn't occur. This is no longer purely philosophical. Physicists are actively testing these ideas using black holes. In the 1970s, Stephen Hawking discovered that black holes emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. This led to the famous black hole information paradox. If a black hole evaporates, where does the information about what fell into it go? According to the holographic view, the information isn't lost. It's preserved on the surface of the event horizon, just like the hologram encodes the 3D image. If true, this principle may apply not just to black holes, but to all of space. That would mean space is, in a sense, an illusion, an effective reality built from something deeper, and if so, asking where space ends is like asking where a rainbow ends. It ends not in a place, but in a perspective, in a condition where the illusion no longer appears. Now, let's return to what we can observe. Astronomers look at the distant universe not with their eyes, but with light. Every telescope is a time machine. The farther we look, the farther back in time we see. And yet, even this vision has limits. Beyond a certain distance, the light becomes redshifted so extremely that it fades into invisibility. Galaxies become ghosts, and then they vanish altogether. And that, perhaps, is a kind of ending. Not an edge of space, but an edge of light. The edge of the visible universe. Beyond it, space may continue, but it lies forever hidden, not by distance alone, but by time. Because space expands faster than light can travel, some regions are moving away so quickly that their light will never reach us. Not now, not ever. This means there are entire galaxies, possibly even clusters, superclusters, and cosmic webs that exist in the universe right now, but will never be part of our reality. They are real but inaccessible. This introduces a quiet, poetic kind of limit. Not a wall, but a silence. Not a barrier, but a darkness. We live in a universe whose observable portion is always shrinking, even as space itself grows. Over billions of years, more and more of the cosmos will fade beyond our cosmic horizon. The universe, it turns out, is becoming increasingly unknowable. This may not be the end of space, but it is the beginning of cosmic solitude. And it brings us to a deeper question. If there are parts of the universe we can never see, never touch, never interact with, do they still count? Are they part of our universe? Or are they functionally separate? Some philosophers and physicists argue that if something is permanently beyond our observational reach, then it may be indistinguishable from something that doesn't exist at all. Others say that reality doesn't depend on observation. The universe, in all its infinite or finite glory, simply is, whether we see it or not. It's a question that touches on the boundary between science and philosophy. What counts as real? What counts as space? And here, perhaps, is where science meets humility. The edge of space may not be a thing we find with telescopes. It may be a limit we reach in our understanding. Not a place we arrive at, but a horizon we see from afar. A line between what we know and what lies forever just beyond. So the next time you gaze at the stars, remember this. What you're seeing is not just starlight. It's the whisper of a universe stretching into the unknown. A universe whose ending may never come, and whose mystery may be its greatest beauty. By now, we've travelled across billions of light years, bent our minds around curvature and cosmic inflation, and even pondered whether space itself is an illusion. But tonight, we go deeper still, not outward toward the far edge of the universe, but inward into the nature of boundaries themselves. Because perhaps the most difficult thing about asking, does space end, is understanding what it means for anything to end at all. Let's start with something deceptively simple. What does it mean for something to end? In everyday experience, an end implies a boundary, a limit, a wall or threshold beyond which something else exists, or beyond which there is nothing at all. Your street ends at a fence. A book ends on its final page. Even a day ends with nightfall. But these are all examples within the familiar rules of life on Earth, a world defined by objects, places, and changes over time. In space, things get more complicated. Imagine walking toward the horizon. As you walk, the horizon always stays ahead of you. You can walk forever, and the horizon will never be reached, because it's not a place, it's a perceptual boundary defined by how far you can see across the curved surface of Earth. In a similar way, many boundaries in cosmology are not physical walls. They are limits of perception determined by light, time, or the nature of space itself. This brings us to the concept of manifolds. In mathematics and physics, a manifold is a space that, on a small scale, looks flat, like the world beneath your feet, but on a larger scale may curve and connect in unusual ways. The surface of Earth is a two-dimensional manifold. You could walk its entire surface without ever encountering an edge, even though the planet is finite. Physicists believe that our three-dimensional space may be a three-manifold, a higher dimensional version of this idea. It could be finite in volume, but without boundaries. You could travel forever in any direction and never encounter an edge, eventually circling back to your starting point without even realizing it. To most of us, this feels strange. We're used to flat maps with edges, but the cosmos is not a map. It is a curved, dynamic entity, expanding, warping, and possibly wrapping back on itself in ways that defy ordinary intuition. If this is true, then space does not end because it doesn't need to. It doesn't require a fence or border. It simply is, complete in its own structure, continuous in its geometry. But what if we insist that space must have an edge? What would that even look like? Would there be a place where space just stops? Where you could point and say, there, that's the end? What lies beyond such a boundary? This idea runs into serious problems. First, if space has an edge, it implies that space exists within something else, like air inside a balloon or water in a fish tank. But space is not in anything. It is not suspended in a higher space. It is not floating in a bigger container. Space is the arena in which everything happens. And so, to suggest that it ends is to suggest that it exists within something else. And that leads to a deeper question. What is that something else? We begin to see how the idea of space having an edge becomes increasingly abstract. It shifts from physics to metaphysics. We are no longer talking about locations and distances, but about definitions and paradoxes. One famous analogy often used in cosmology is the surface of a balloon. Imagine that you are a two-dimensional creature living on the surface of an expanding balloon. You can move in any direction, and the balloon's surface stretches as you do. From your perspective, the universe is expanding, but there is no edge. You are bound to the surface. You can't fall off. You can't reach an outside, because the outside exists in a third dimension that you don't perceive. In this analogy, the third dimension stands in for a higher dimensional space that our universe might be embedded in, or not. The point is, the expansion doesn't require a center or an edge. Every point on the surface moves away from every other point, and yet the surface itself is finite and without boundary. Now, in our real universe, we live in 3 spatial dimensions. But if space is curved in 4 dimensions, or higher, we might never perceive that curvature directly. We might be like the 2D creatures on the balloon, sensing only the local properties of space, while its true shape remains hidden from view. This leads to one of the most profound challenges in all of science. Our experience is limited by our dimensionality. We are beings bound to perceive 3 spatial dimensions and 1 temporal one. All our thoughts, languages, and instruments are designed around this framework. But reality may be deeper. If there are extra dimensions, as string theory suggests, then space might extend or loop through them in ways we can't imagine. In some string theory models, space is made of tiny vibrating strings existing in 10 or 11 dimensions. Most of these dimensions are compactified, curled up so tightly that they are invisible at human scales. But their presence could affect how gravity works, how particles interact, and how the universe evolves. Could space end in one of these hidden dimensions? Could we pass through a region where the familiar 3 dimensions dissolve and the higher structure of the universe becomes apparent? We don't know, but the fact that such questions can be asked and studied speaks to the incredible depth of modern theoretical physics. But let's return to what we can measure. One of the tools we use to explore the structure of space is gravitational lensing. When light from a distant galaxy passes near a massive object, such as a galaxy cluster, the gravity of that mass bends the light, just like a glass lens. This effect, predicted by Einstein's theory of general relativity, allows us to map the curvature of space itself. By studying gravitational lensing on large scales, we can infer whether space is curved positively, negatively, or not at all. So far, the evidence points to a flat universe, at least across the observable scale. But flat does not mean infinite. It simply means the rules of Euclidean geometry, the geometry we learn in school, still apply. And within that geometry, both infinite and finite configurations are possible. So even now, we don't know for sure. Space could be infinite, stretching endlessly in all directions with no repeating patterns and no limit. Or it could be finite but without edge, like a cosmic loop. We simply don't have the tools yet to decide. This brings us to the topic of cosmic topology, the study of how space is connected on the larger scales. If space loops back on itself, We might expect to see repeated patterns in the cosmic microwave background, the faint glow left over from the Big Bang. Imagine looking in opposite directions and seeing the same galaxy repeated across the sky, because light from that galaxy has traveled around the universe more than once. It would be like living in a hall of mirrors, seeing echoes of distant light that has circled the cosmos. So far, no such repeating structures have been detected, but the search continues. If these patterns are found, it would be one of the greatest discoveries into history. Proof that space is finite, closed, and connected in a way we can directly observe. But if we don't find such patterns, it doesn't mean space is infinite. It just means the loops, if they exist, are too large or subtle for us to detect. And so we find ourselves at the edge, not of space, but of knowledge. Our instruments can only see so far. Our theories only reach so deep. Beyond that lies a realm we cannot yet touch. Perhaps because it is too far, or because it is made of something we don't yet understand. Still we look. Still we ask. Still we wonder whether the space ends, and what it means if it doesn't. And maybe that's the real beauty. The universe doesn't give up its secrets easily. It invites us to think harder, look deeper, and stretch our minds beyond the familiar. If space doesn't end in the way a road or a hallway does, then why do we often feel like there must be an outside to everything? Why is it so hard to grasp the concept of a boundaryless, continuous universe? This question touches on something deeper than astronomy. It touches on how human minds evolved to interpret the world. Our brains developed to navigate forests, find shelter, and sense danger, not to comprehend 10-dimensional manifolds or infinite geometric surfaces. We're wired for survival, not cosmology. So when we ask, does space end? We're really asking, where are the limits of what I can imagine? In this part of our journey, we'll explore how human perception shapes our understanding of space, and how space, in turn, challenges everything we believe about beginnings and ends. Let's begin with a mental experiment. Close your eyes and imagine floating in deep space. There's no planet, no star, just darkness and silence. Now imagine traveling in a straight line, forever. Would you eventually reach a wall? Would the stars run out? Or would you find yourself circling back? It's hard to picture. Our imaginations resist the idea of endlessness, just as they resist the idea of something coming from nothing. Even scientists struggle with this. Einstein himself was uncomfortable with the notion of a universe that had no edge. When he developed general relativity, one of his first instincts was to apply it to a static universe, eternal and unchanging, with a neat, closed geometry. But when Edwin Hubble showed that galaxies are moving away from one another, that the universe is expanding, everything changed. Suddenly, the cosmos wasn't static or eternal. It had a history, a beginning, and possibly an end. But even that beginning, the Big Bang, doesn't mean what it sounds like. The Big Bang wasn't an explosion in space, it was an expansion of space itself. All of space, everywhere, growing from an unimaginably hot, dense state. There was no outside to it, no center, no edge. The Big Bang happened everywhere at once, because everywhere was contained in it. This is one of the hardest concepts in cosmology to wrap your head around, but it's key to understanding why space might not end, not because it stretches forever like a flat sheet, but because it's all there is. There's nothing for it to end into. Still, we crave some kind of visual, some way to frame the idea. One helpful analogy is the Pac-Man universe. Imagine the old arcade game where Pac-Man disappears off the right side of the screen and reappears on the left. In this two-dimensional world, space is finite. The game map has limits, but it loops. If you keep walking in one direction, you eventually return to where you started. Now imagine a three-dimensional version of this. You travel in a straight line through the universe and eventually end up back where you began. You wouldn't notice the transition because space is smooth and seamless. But the universe would still be finite, like a cosmic video game map that loops endlessly. This kind of looping space is known as a multiply-connected topology, and it's not just science fiction. Some models of the universe, like the Poincaré dodecahedral space, suggest that space may be finite and connected in exactly this way. In such a universe, the same galaxy could appear in multiple places in the sky, just like a repeating tile pattern. Light could take different paths around the loops, arriving from different directions. If we could detect these repeating patterns, we might finally learn the true shape of space. And yet, despite decades of searching, we've found no conclusive evidence for this kind of repetition. The cosmic microwave background, our most ancient map of the universe, shows remarkable uniformity. No clear signs of cosmic looping, no echoes of galaxies seen more than once. But absence of evidence is not evidence of absence. The loops may be larger than the observable universe, or the shape may be more complex than we can currently detect. What we do know is that space behaves according to the rules of general relativity, and that those rules allow for many possibilities. Infinite flat space, closed curved space, or something in between. Let's now consider another possibility. Space is not fundamental at all. This may sound strange, but some physicists believe that space, like temperature or pressure, is not a primary ingredient of reality. Instead, it may be emergent. Just as temperature emerges from the motion of molecules, space may emerge from something deeper, perhaps from quantum entanglement, or from information itself. In these models, the fabric of space is like a hologram, a pattern of information encoded on a lower dimensional boundary. This is known as the holographic principle, and it's one of the most radical ideas in modern physics. In a holographic universe, the true description of reality takes place not within space, but on the edge of it, in a kind of cosmic code that gives rise to everything we see. Space, distance, and even time would be illusions, useful approximations that emerge from deeper rules. If this is correct, then asking "does space end?" is like asking whether the temperature of a video game character ends at the edge of the screen. It's not a meaningful question because the temperature and the space are not real in the fundamental sense. They are simulated, emergent, derived. This doesn't mean they're fake, it just means they are constructed, built from something deeper. And if space is constructed, it may not need to end. It may simply be a region of the universe where the emergent properties we call space exist. And beyond that region, the concept may lose its meaning entirely. Another radical idea comes from the study of black holes. Black holes challenge our understanding of space in profound ways. According to general relativity, a black hole is a region where space is so curved that nothing, not even light, can escape. The boundary of this region is called the event horizon. But what happens inside a black hole? According to some models, the interior of a black hole may not just collapse into a point. It may instead connect to another region of space, like a bridge or a tunnel. This is known as a wormhole. If wormholes exist, they could allow space to connect in non-traditional ways, forming shortcuts between distant regions or even between different universes. It's still speculative, but if true, this would mean that space is not a flat sheet, but a tangled web, full of connections, loops, and tunnels that defy ordinary logic. Space, in this view, is a dynamic, ever-changing structure, capable of stretching, folding, tearing, and reconnecting. It doesn't need to end because its very nature resists fixed boundaries. And then, of course, there's the multiverse. In some interpretations of inflationary cosmology, our universe is just one bubble in a vast foam of universes, each with its own space, laws, and history. If that's true, then the end of our space might simply be the edge of our bubble, beyond which lies other realms, inaccessible and unknowable. This doesn't mean you can fly there. The bubbles are not embedded in a shared space. Each has its own space-time. You can't travel between them, at least not with our current understanding of physics. But the idea of a multiverse again forces us to ask, what is space really? Is it local to each universe? Or is there a deeper structure from which all space arises? Once again, we find ourselves staring into the unknown. And perhaps that's the point. The mystery of whether space ends is not just a question of physics, it's a question of perspective. It reflects our desire to understand our place in the cosmos, to know whether the world has boundaries, and if so, what lies beyond them. But maybe the most astonishing thing isn't what we don't know, it's what we do. We know that space can curve, that it can expand, that it can ripple with gravitational waves. We've mapped galaxies 13 billion light years away. We've watched black holes merge in the distant dark. We've measured the afterglow of the Big Bang, the light of creation itself. Imagine for a moment that you could step outside of our universe, not metaphorically, but truly beyond it. What would you see? Would you find yourself surrounded by a vast emptiness? Would other universes drift nearby like bubbles in a cosmic ocean? Would you feel gravity, see light? Or would all our familiar concepts, distance, direction, time, simply dissolve? We don't know, and that's what makes this question, does space end, so endlessly fascinating. In this part, we journey further into speculative but scientifically grounded territory. What might exist beyond the observable universe? And how do we even define a beyond? Let's begin with what we can see. The observable universe is the portion of the cosmos we can access with light. Because light travels at a finite speed, about 300,000 kilometers per second, we can only see as far as light has had time to travel since the universe began, around 13.8 billion years ago. But space has been expanding during that time, so even though the universe is 13.8 billion years old, the most distant light we see today comes from galaxies now over 46 billion light years away. This defines our observable horizon, a sphere centered on Earth stretching about 93 billion light years across. But that's not the whole universe. Far from it. There's no reason to believe the universe ends at the edge of the observable bubble. In fact, most cosmologists agree that space continues far beyond, perhaps infinitely, or at least unimaginably far. It's like standing on a foggy plain. You can only see so far in each direction, but that doesn't mean the landscape ends at the edge of the fog. It simply means your view ends there. So what lies in the fog? To answer that, scientists use the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. In simpler terms, matter is distributed roughly the same everywhere, and the laws of physics are the same no matter where you go. This principle, supported by astronomical observations, allows us to infer what likely lies beyond our observable limit. If true, the universe beyond what we can see probably looks very similar to what we can see. Galaxies, stars, dark matter, cosmic filaments, and voids. a continuation of the same vast cosmic web. But we must be careful. This assumption, though useful, is unprovable. We can't test it directly because we can't observe what lies beyond light's reach. And in science, what can't be tested remains a hypothesis. So again, we find ourselves circling the question, does space end? To explore this further, we need to understand a subtle but powerful concept: comoving coordinates. In an expanding universe, distances between distant objects grow over time, even if the objects themselves aren't moving through space. This is not motion in space, it's motion of space. To track this expansion, cosmologists use comoving coordinates, a mathematical tool that stretches with the universe, allowing us to describe positions that stay in place relative to the cosmic expansion. With this framework, we see that the universe may be spatially infinite, meaning that even though we can only observe a finite part of it, the total extent of space could be unbounded. In an infinite universe, every arrangement of particles that can happen must happen, somewhere, eventually. This leads to a strange idea known as the infinite monkey theorem, applied to cosmology. If space goes on forever and the laws of physics allow only a finite number of arrangements for matter in any given region, then eventually the same patterns repeat. That means there could be another Earth, perhaps an entire duplicate of you, unimaginably far away, living a life indistinguishable from your own. It's not science fiction, it's math, pure probability stretched across endless space. And if that doesn't make you pause, consider this. In an infinite universe, not only do duplicates exist, they exist infinitely many times. There is no original, just endless variations. But what if the universe isn't infinite? Some cosmological models suggest that space might be finite, but unbounded, like the surface of a sphere. In these models, you could travel in one direction forever and eventually return to your starting point, much like a plane flying around the Earth. Again, there would be no edge, no border, just a looping, self-contained cosmos. So how do we distinguish between infinite and finite but boundless space? It's incredibly difficult. Our observable universe is simply too small compared to the total to tell the difference. Still, scientists search for clues. For example, a finite universe might show matched circles in the cosmic microwave background, echoes of light that traveled around space and met itself. These signatures would be faint, but not impossible to detect. So far, no definitive evidence of such patterns has been found, but the search continues. Now let's turn to a more radical idea: cosmic inflation. Inflation is the theory that in the first tiny fraction of a second after the Big Bang, the universe expanded exponentially, far faster than the speed of light. This rapid inflation would explain many puzzles: the smoothness of the cosmic microwave background, the flatness of space, and the absence of magnetic monopoles. But inflation has a consequence. In most versions of the theory, inflation never truly ends everywhere. It ends only in localized regions, like pockets, while the rest of space continues to inflate. This process creates a multiverse, an infinite mosaic of bubble universes, each with its own physical constants, particles, and space-time structure. In this scenario, our observable universe is just one bubble in an endless froth of others. Each bubble could contain entirely different laws of nature. Gravity could be stronger, time could flow differently, or space might not exist at all. If this view is correct, then the question, does space end, becomes even more complex. Does our bubble have an edge? Yes, in a way, the boundary where inflation continues. but you could never reach it. The space between bubbles expands faster than light, making them causally disconnected. No ship, no signal, no thought could ever cross. And yet, in a grander sense, space itself, the canvas on which all bubbles float, continues forever. Of course, this too is speculative. We have no direct evidence for other bubbles, but the math holds up, and many physicists take it seriously. Now take a step back. We've explored infinite space, finite space, emergent space, holographic space, and inflating space. We've discussed duplication, repetition, topology, and cosmic boundaries that may not even exist. And yet, after all that, the question remains unanswered. Why? Because space is not just a place. It's a concept, a framework, a structure we impose to make sense of relationships between objects, between events, between ourselves and the cosmos. So when we ask whether space ends, we're also asking about the limits of thought, the boundary between the known and the unknowable, the point where our instruments, our theories, and even our language reach their limits. And yet, we keep asking. That's the remarkable part. We keep building bigger telescopes, running deeper simulations, writing more elegant equations. We keep listening to the sky, not because we expect to hear a final answer, but because the question itself is beautiful. So as we float onward in this ocean of thought and stars, we don't need a solid answer to rest easy. Why do we even ask whether space ends? It's not just curiosity, it's a longing for structure, for boundaries, for a sense of place in something that feels overwhelmingly vast. We crave answers to anchor ourselves. So far, we've explored the observable universe, the potential for infinity, the possibility of bubble universes, and the concept of space as an emergent property. But there's another thread we haven't followed closely yet: the role of geometry itself. What shape is the universe? In mathematics, the geometry of space can be curved or flat. This curvature tells us a lot about whether the universe is infinite, closed, or open, and possibly whether it ends. We start with the idea of spatial curvature in three possible forms: positive, negative, and zero. If the universe has positive curvature, it's like the surface of a sphere. In this case, space is finite. You could travel in one direction and eventually return to your starting point. There's no edge, just a continuous loop. This is a closed universe. If the universe has negative curvature, it's like a saddle, open, with space curving away in all directions. This type of universe would be infinite in extent, expanding forever with no looping paths. And if the universe is flat, like an endless sheet, it could also be infinite, or it could be finite, but wrap around itself in a torus-like topology, like a video game world that scrolls seamlessly from one side to the other. So which is it? According to the Planck satellite and other cosmic microwave background observations, the universe appears to be remarkably flat, with any curvature being so slight that we can't yet detect it. This strongly suggests either an infinite universe or a very large finite one with a flat geometry. But flatness doesn't guarantee infinity. The Earth too feels flat beneath our feet, yet we know it's round. We simply live on a small enough patch of it. Likewise, the observable universe may just be a tiny part of a much larger, curved whole. And this brings us to another important idea: topology. Geometry tells us about the curvature of space, while topology tells us about its connectedness. Think of topology like the shape rules of the universe, whether it loops, whether it has holes, whether it wraps around itself. Some topologies allow a finite universe with no edges, like a 3 torus, essentially a 3D version of a donut. In such a universe, if you travelled in a straight line long enough, you might return to your starting point. Space would loop in all directions, but you wouldn't see a wall or boundary. There would be no end, only continuity, like walking endlessly on the surface of a globe. So even if the universe is finite, it might still feel infinite to anyone inside it. And yet our tools are limited. Even the deepest space telescopes can only observe so much. If the universe is much larger than the observable bubble, whether infinite or just very big, we might never see the full picture. Now, let's entertain a more radical thought. What if the universe does have an edge, not just metaphorically, but physically? It seems impossible. General relativity, our current best theory of gravity and space-time, doesn't allow for a traditional edge. The equations break down at a boundary, like a map suddenly running out of paper. But some speculative models propose the existence of a brane, a boundary-like structure in higher dimensional space. In string theory and related models, our universe could be a 3D brane floating in a higher dimensional bulk. In this view, there may be an edge, not in our 3 dimensions, but in the broader structure in which our universe is embedded. And what lies beyond that edge? Other branes, other universes, or perhaps nothing at all. That word, nothing, is one of the most mysterious in all of physics. What does it mean for there to be nothing? Not empty space, not vacuum, not even potential energy. Just absence. Is that even possible? Some physicists argue that nothing is actually unstable. According to quantum theory, even the most perfect vacuum is never truly empty. Tiny fluctuations, called quantum foam, constantly bubble into and out of existence. These fluctuations can give rise to particles, forces, even whole universes. In this sense, space and the universe could emerge from nothing in a burst of quantum activity. The end of space, then, might be a place where space hasn't yet emerged, or where it cannot exist. But again, we must tread carefully. These are theoretical landscapes, beautiful but untested. Even if such edges exist, we may never be able to reach them. The cosmic expansion ensures that the farther we look, the faster things recede from us. Beyond a certain distance, galaxies move away faster than light, not because they're moving through space, but because space itself is stretching. These regions are forever beyond our reach, not because of technology or travel, but because the structure of reality itself draws a curtain we cannot lift. And this leads us to a poetic truth. Perhaps the universe doesn't end with a bang or a wall or a drop into nothingness. Perhaps it ends with silence, with the slow fading of galaxies beyond our grasp, with the dimming of starlight that will never reach us, with the quiet retreat of meaning into the horizon. It's possible that space has no sharp edge, only a gentle fade into unknowability, that our desire to find an end is like looking for the edge of the ocean while floating in the middle of it. As we continue our slow drift through the question, does space end? Let's follow a quiet but compelling thread: the relationship between space, time, and perception. So far, we've treated space as something external, something physical and real. But what if space is a reflection of something else? What if space is not fundamental, but emergent, a kind of illusion born out of deeper, hidden patterns? To understand this, we turn to quantum gravity, the ongoing effort to reconcile Einstein's general relativity with the strange behavior of quantum mechanics. These two pillars of modern physics, while both incredibly successful in their domains, don't yet play nicely together. General relativity describes space as a smooth, continuous fabric. Quantum mechanics, on the other hand, deals in uncertainty, superposition, and probabilities. When we try to apply both at once, especially at extreme scales like black holes or the beginning of the universe, the math breaks down. That's where theories like loop quantum gravity, causal set theory, and string theory come into play. Let's gently explore one of these: loop quantum gravity. In this framework, space is not continuous, but made up of tiny, indivisible loops, like a fabric woven from threads of quantum information. Imagine that space itself is pixelated, though at a scale far too small for us to ever detect directly, smaller than a proton by a factor of a billion. In this view, space emerges from the relationships between quantum events. It's not a background stage where things happen. It's the product of interactions. There is no absolute out there. There is only what is measured, what is related, what is observed. This idea becomes even more radical in entropic gravity, a theory that proposes gravity is not a fundamental force, but an emergent property of information moving through space. In this model, space itself arises from the distribution of information, like heat emerging from molecules in motion. The structure of space may simply be a result of how information is stored, shared, and perceived. And what does that mean for the edge of space? It means the end of space might not be a place, but a limitation of perspective. If space is emergent, then its extent depends on the information available to the observer. Like a dream, it only stretches as far as your mind can build it. Now let's bring black holes back into the picture, because they offer an especially compelling lens through which to view the boundaries of space. Black holes represent a kind of edge, not an end to space in a classical sense, but a limit to what can be known and experienced. At the event horizon of a black hole, light itself cannot escape. Any information that passes through is cut off from the rest of the universe. From the outside, time appears to freeze. The black hole becomes a boundary, a one-way membrane that divides what can be reached from what can't. But the story doesn't end there. According to quantum mechanics, information must be preserved. This leads to the black hole information paradox, which has puzzled physicists for decades. Where does the information go? Does it truly vanish inside the black hole, or is it somehow encoded on the surface? Enter the holographic principle. This astonishing idea suggests that all the information contained within a volume of space can be encoded on the boundary of that space, much like a hologram stores 3D information on a flat surface. In other words, our entire three-dimensional universe might be a projection of two-dimensional data on a distant boundary. Let that settle in for a moment. If the holographic principle is correct, then space is not as it seems. What we perceive as depth, distance, and volume might be a kind of illusion, a reflection of deeper mathematical structure. So if space is holographic, does it end? It might not have to. The projection can continue as long as the underlying data exists. The boundaries of space become boundaries of information, not of matter or motion. The edge is not a wall, but a resolution limit. Like trying to zoom too far into a digital image, eventually the pixels reveal themselves. And still, there's more. We must remember that our understanding is shaped by our senses. Our eyes, our instruments, even our equations are filters, tools we use to interpret reality. But the universe may be operating on levels we can't yet access. Just as ants on a sheet of paper can't perceive a balloon floating above them, We might be blind to dimensions just out of reach. String theory, for example, proposes the existence of extraspatial dimensions, curled up so tightly that we don't experience them directly. These dimensions could play a critical role in shaping the universe as we know it. If space truly extends into these higher dimensions, then our question becomes more complex. Does three-dimensional space end, or does it simply curve into another realm? Perhaps what we experience as boundaries are really folds, curves in a multi-dimensional geometry we're only beginning to glimpse. And so we return again to the metaphor of the horizon. No matter how far we look, there's always a limit. Not because the universe ends, but because light takes time to travel. The cosmic horizon is like a fog, not a wall, but a veil. Beyond it, more galaxies, more stars, more mysteries may lie. But we will never see them, not because they're not real, but because they're moving away from us faster than light can bridge. In a way, the universe may continue forever, and yet we will always live within a shrinking bubble of knowability. And so, here we are, at the quietest edge of our exploration. We've travelled through expanding universes, curved geometries, quantum foams, invisible boundaries, and perceptual limits, all in search of an answer to a single question: does space end? The truth, as we've discovered, is both comforting and humbling. Space may not end in any traditional sense. There are no walls at the edge of the cosmos, no cliffs overlooking a void. Instead, what we encounter are limits of perspective, boundaries of time, constraints shaped by the speed of light, by gravity, by entropy, and by the tools we use to understand. But despite these limits, or perhaps because of them, the universe remains infinitely rich. Consider the expansion of space, how galaxies are carried ever outward on the swelling fabric of the cosmos. This expansion stretches the very light trying to reach us, dimming and redshifting it until it fades beyond detectability. Some galaxies are already beyond that reach, still real, still out there, but forever invisible. In this way, the observable universe is not a cage, but a candlelit dome, a warm, softly glowing horizon marking what we can see, not what is. And then we learned about dark energy, the mysterious force driving this expansion faster and faster, perhaps accelerating us toward a future where fewer and fewer galaxies remain in view, where the night sky empties, where only local clusters linger, a future that feels more intimate but also more isolated. Yet even then, we would not be at the end, just in a different room of a very large house. Even the idea of nothing, the vacuum, turns out to be full of potential. In quantum mechanics, empty space seethes with uncertainty. Particles flicker into existence and vanish. Virtual fields jitter with activity. What appears to be stillness is actually alive with probability and energy. If this is what nothing looks like, perhaps space itself is never truly empty, never finished. Even black holes, which once seemed like ultimate endpoints, may not be as final as we believed. If Hawking radiation causes them to evaporate over time, they are not eternal prisons, but temporary pockets. If information can be preserved, encoded in holographic surfaces, then not even the most extreme regions mark a true boundary. Everywhere we looked for an edge, we found a doorway. So what are we left with? A sense that space, as we know it, may not end, not because it stretches forever, but because it's always becoming, always in process. What we perceive as distance is woven from relationships. What we experience as vastness is rooted in consciousness. Maybe space is not just a stage where matter moves. Maybe it's a language, a rhythm, a mirror, and in that mirror we see ourselves. We are made of atoms that once danced in stars, scattered across the cosmos by ancient supernovae. The iron in your blood, the calcium in your bones, the carbon in your breath, all were born in space. You are not separate from the universe. You are its echo, its question, its momentary self-awareness. Even the act of wondering, does space end, is part of the universe's ongoing expression, the cosmos asking itself who and where and what it is. So tonight, as you lie back and drift into stillness, consider this. You are not floating in space. You are space folded into the shape of a dreamer. Your thoughts, your breath, your heartbeat, they ripple outward into the vast unknown, joining every photon, every particle, every possibility. Let the immensity hold you, not as something separate, but as something remembered. Let your curiosity become calm. Let the mystery become comfort. Let the question fade, for now, into the quiet. Because even if we never find the end of space, even if it turns out there is none, the journey of asking has already brought you here. To this moment, this breath, this soft science. Sleep well, traveller of the stars.